topic for the presentation today is determining hydrate phase boundary. And I think we need more than one session to cover it. As we discussed earlier, hydrate is solid compound formed as a combination of water and gas molecule. For formation of hydrate, we need the presence of water or ice, suitable size gas or liquid molecule like methane, ethane, propane, isobutane, CO2, etc., and suitable condition of pressure and temperature condition. Now, the suitable condition for pressure and temperature is presented in this figure. This is a suitable condition. And this is probably the first thing that an engineer will do. To the left, we have hydrate. To the right, we don't have hydrate. So we need to find out this curve first. The location of this curve depends on two parameters. It depends on hydrocarbon composition, gas liquid composition, and water composition. For hydrocarbon composition, the different molecules, they have different affinity to form hydrate. So this is affinity of two molecules to form a mixture or to form hydrate. If one of these molecules is water or oxygen, and the other one is a gas, when they are far away from each other, then they don't form any hydrate. They don't have any reaction. But if they get close to each other, they are attracted to each other, and if they get close too much, they have repulsion. In hydrate crystal, the position of oxygen molecule is fixed. This is oxygen, hydrogen, oxygen, hydrogen, and then oxygen. So the distance depends on the size of molecule. If the molecule is too small, it's difficult to form hydrate. So a molecule like hydrogen or nitrogen, they are too small, and it's very difficult to form hydrate. But if the molecule is large, then the attraction here is strong. Therefore, they can form hydrate. If it is too large, then they get very close to each other and the repulsion will work. This section will work. So one depends on the composition of the hydrocarbon phase. The other one is the composition of the aqueous phase. If there is anything dissolved in the aqueous phase and is not a hydrate former, for example, glycol, then some water molecules are busy dissolving them. So it is less water molecule available for hydrate formation. So the hydrate curve shifts to the left. And if you have butane or H2S are very easily forming hydrate. The hydrate curve shifts to the right. It's easier to form hydrate. But if we have nitrogen, the hydrate curve moves to the left. So because it is more difficult to form hydrate. So the key point is to determine the hydrate phase boundary. And this phase boundary we can determine in two ways. First of all, I need to say that there are three hydrate structures. Structure 1, structure 2, and structure H. And here determine the composition of different structure. For example, 2 small molecule and 6 large molecule here form structure 1. 16 small molecule and 8 large molecule form structure 2. Obviously, here the large molecule has 15 sides. From this 12 sides, from these 12 are pentagonal. They are pentagonal. Here we have 14 sides, and then here 12 of them are pentagonal, 2 of them are hexagonal. Here you see that it has 16 of this pentagonal and 8. This is basically, you can see that they have 12 pentagonal and 4 hexagonal and structure 2. And here we have 3 small molecule which has 12 pentagonal faces, and then 3 with 4 phases, 6 with 5 phases, and 3 with 6 phases, 2 of these, 3 of these, and 1 of these large molecule form structure 1. Now, a small molecule normally form structure 1. A slightly bigger molecule, they form structure 2, and very large molecule form structure H. So that is ability to form hydrate structure, but there is another factor that from energy viewpoint, which one is easier to form. And that is something that we will discuss later. So when hydrates form, to change the point. Here is hydrate formation. You can see is water and gas, and this was the thermometer. And the diameter of the thermometer is 3 millimeter. So you can see that hydrate forms at the interface. And this is a water phase. And this is the gas phase. A layer of water is on the wall of the glass window. And as you see here, we form hydrate. This is hydrate formation from dissolved CO2. So there is no gas phase. This is water that we dye it with blue, and this is hydrate. And see that how will that progress. Here we adjust the pressure and stop, and then increase the pressure again. So hydrate can form from gas dissolved in water. So if you don't have a gas phase, it doesn't mean that you don't form hydrate. But because solubility of gas in water is small, then the amount of hydrate could be small. But here CO2 has a high solubility. Thus you see that the amount of hydrate is quite a lot. And you see that it has various branches to hydrate formation, exothermic. So want to get rid of the heat, and also needs to get other gas molecules to form hydrate. This is a mixture of gas and hydrate and water. So here you can see that how here you see that the hydrate is glowing. Here water is dissolving in gas is dissolving in water and contributing to hydrate formation. Now here you can see that the gas is shrinking. Here is formed hydrate, and now it is growing from here, and this gas is shrinking and forming hydrate. So you see that the gas doesn't need to be at the point of hydrate formation. The gas by diffusion can go to the point of hydrate formation. This is melting. Here we injected MEG, and you can see that how MEG will dissolve hydrate and how the gas molecule evolve from hydrate. You see that here? And you see the majority, because from the bottom of view, because MEG is heavy component, heavier than water, and will be in the lower part of the cell. Here demonstrating that hydrate is source of energy, and you can see that hydrate is in the hand of my colleagues, and you can see that hydrate is producing gas and maintaining the flame, and you can see that how the water comes out from melting hydrate. You can see that the water here. So we discussed this figure before. This is the phase envelope. This is a bubble point. Let me go back to my pointer. This is the phase envelope, and this is the bubble point. This is the dew point. This is reservoir condition, and as fluid is produced to surface, the pressure and temperature of the system will change, and you see that here barium sulfate can form, and then here the bubble point. So up to here is a single phase. Here is we have some gas phase, and then here we go into the asphaltene phase boundary. Here we go into the wax phase boundary, and now we go into the hydrate phase boundary. Our objective here is to calculate or to determine hydrate phase boundary. So we want to determine the hydrate phase boundary here. So there are various options to determine hydrate phase boundary. One is experimental. For experimental, we have to measure hydrate phase boundary or determine whether we have reached hydrate phase boundary either visually or graphically. In the past, used to be visual, but now because of safety, we prefer to have graphical or combination of the two, so we don't need to look at the window to avoid any accident. There are three techniques we discussed before: isothermal, isobaric, isochoric. So more popular one and much easier to use for visual and graphical is isochoric. Isochoric means that we have a volume of hydrate in the system or hydrate forming component in the system. We don't change that, okay? The other option is modeling. Modeling, there are different options again: gas gravity method, distribution coefficient method, or a statistical thermodynamic approach. Now, these are very old methods, you know, we can discuss them, but at the moment, normally, we don't use that, you know, and we use a statistical thermodynamic approach. So, experimental measurement, here, pressure and temperature, and we cool down the system. We cool down the system. Here you see the pressure drop. Initially, pressure drop is because of, you know, a straight line, roughly, because of the volume reduction, because of temperature change. So you have some gas component here. As the temperature drop, the volume is reduced, and we can totally predict this one. And then here you see that sudden decrease in the pressure, and that as a result of hydrate formation. So here the point that hydrates has formed. And this, we are melting hydrate. You see that this is parallel to here. So this is gas expansion, but here is that slope has changed, is a start of hydrate melting. And then here you see that we go back to this curve here, this line here, and this is the point that the last hydrate crystal has melted. So this is hydrate formation, this is hydrate dissociation. So which one should we use? Hydrate formation depends on rate of cooling, reactor type, surface type, presence of foreign material. So it's not a fixed number. It can change from one experiment to another one. Hydrate dissociation, if we do the test carefully, is unique. Hydrate dissociation is used for thermodynamic modeling. And it means that at any point inside hydrate formation curve, inside the hydrate curve here, there is a chance of hydrate formation. And because hydrate normally from a small molecule, then when it starts forming, we can have significant of hydrate, as you saw in the video. So this is the point for design. Now, how to do, I mentioned that if the hydrate dissociation perform correctly, and we will have a unique point. And that is what I meant here. If you increase temperature to melt hydrate, you are not within hydrate stability zone, because you are heating and heating and heating. The point you get is here, which is wrong. So we proposed in 1991 or 2 what is called a step heating. So you heat the system, wait for the pressure to equalize, because that's the point that the last crystal of hydrate melted. So another one here, increase the temperature by 1 degree and then wait for the hydrate to melt. Now these are equilibrium points. Another degree, waited to melt. Another degree, waited to melt. And this is called step heating. And a step heating, then if you connect these two together, that we should determine the correct hydrate dissociation point. Now, for hydrate dissociation, for hydrate phase boundary determination, we need at least 3 to 4 points. Here I'm showing this. We normally start with lower pressure and then gradually by moving piston increase the pressure, or we introduce more gas or to increase the pressure. Here you can see that this is hydrate dissociation point for this here, and another one here, another one here, and another one here. These points can be used for tuning the module or amount of inhibitor or whatever we want. So, and then if we don't know characteristic of a compound, we can find out. In this case, there is a hydraulic fluid that we want to make sure that it doesn't form hydrate inside the umbilical. So here you can see that we know that, for example, at -20, at this condition, 800, hydrate will not form. Okay, so we determine what is the hydrate phase boundary in the presence of that chemical. Now we want to know hydrate phase boundary for pure component. This is experimental measurement, because in order to understand how the system will behave, we need to have for pure component and then decide how to predict the behavior of each component in the system. I mentioned that the components which are very small do not tend to form hydrate. Components which are large enough, they can form hydrate. So here you can see that this is for H2S. You see that there is a sharp increase in the slope. And this one is for ethane, straight line, and then sharp increase. And this is for methane. Okay. What is the reason for sharp increase in the slope is here, if you plot the bubble point of methane, you see that here below this bubble point, this is a gas, and above that is liquid ethane. So when the phase changes, the slope changes here. And here, this is phase change for H2S and slope change for H2S. So now you see that the strongest among these three compounds, the strongest hydrate former is H2S. After that is ethane, and after that is methane. But when they become liquid, it's a different story. So if I do the same for other component, and you can see that I get for H2S, this is for isobutane, this is for propane, this is for ethane, this is for CO2, and this is for methane, and this is for nitrogen. You can see that different components have different tendency to form hydrates. You can see that the strongest one is H2S. After that, in this component that we have here, 7 components. After that is isobutane. After that is propane, and then ethane, and then CO2, and then methane, and then hydrogen. So now you can guess what will happen if you have mixture of these components. But in a hydrocarbon system, you don't have pure component, you have a mixture of components. If you have a mixture of components, then you have a phase envelope. Okay, so here is phase envelope if we have a mixture of components. This is bubble point line, this is critical point, and this is dew point. And this is hydrate phase boundary. Here you see that 0 is here. So ice hydrate vapor. This is liquid water hydrate vapor. And this is the lower point that's that 4 phases can be present. The 4 phases, this is 0 degree, this is ice, hydrate, vapor, and liquid water. Yeah, that's the lower 4-phase portable point. Here, if the ice is melted, become water. So this is water, hydrate, and vapor. And here goes inside two phase. And here we form a liquid hydrocarbon. So phases would be water, liquid hydrocarbon, hydrate, and vapor. We call it upper quarter point. And then here is 4 phase up to here. This is bubble point. Above bubble point, all the vapor become liquid. So now we have liquid water, liquid hydrocarbon, and hydrate. So the objective of prediction is to determine this hydrate phase boundary. And you saw that for a pure compound was easy. Now we want to talk about mixture. Now, there are various options, as I said, for measurement. One is prediction, gas gravity method, and there are charts and correlation. Another one is K value, that basically extension of the K value from liquid and vapor hydrocarbon. And we can do that one. But now we use thermodynamic approach, and the approach we have is a general multi-phase flash. In multi-phase flash, we say that point of equilibrium is when the chemical potential of component, each compound, at different phases are equal. Now, component 1, component I, in phase 1 should be equal to component I chemical potential in phase 2, and then the same component as phase pi. For isothermal system, that become fugacity equilibrium. Fugacity is the best described as escaping tendency. We want to measure fugacity, and that is escaping tendency of component 1 as phase 1, component 1 as phase 2, and component 1 as phase 3, or any number of phases. So if they are equal, then we have reached equilibrium. The problem is now to measure fugacity and make sure they are equal. Now we have two other equations that Z in the is combination of mole fraction and composition of different components in different phases. So for example, if we have Zi, I is methane, methane can be in hydrate phase, can be liquid hydrocarbon phase, it can be in the gas phase, can be in the water phase, but they should have the same fugacity. But the combination of methane in different phases is equal to amount of methane in the feed. So this is component balance, okay? But in each phase, we can have material balance, the more fraction of each compound at each phase should be equal to 1. From these two and this equality of fugacity, we will end up having number of phases multiplied by a number of components plus 1 equation. And now we can solve this equation in two approaches. One is that we can fix temperature. We can fix temperature and find the pressure of hydrate formation. So we say that, okay, 5 degrees, what is the hydrate formation temperature? We find it. Another option is that to fix pressure and find temperature that form hydrate. So this is basically, we are determining hydrate phase boundary. Hydrate phase boundary is the point that actually hydrate is 0, but just about to form hydrate. Okay? So this is hydrate phase boundary. The other option is flash calculation. Flash calculation, we give temperature and pressure and find amount of the composition in different phases and number of phases. Okay? We find the number of phases and composition of each phase. So these are the two types of calculation we can do. Now, the point is that now we need to find out how many phases we can have. In a typical hydrate problem, we can have these phases. We can have gas phase, we have aqueous phase, that we can have salt, we have methanol, we have glycol, we have ethanol. So this can be very complicated, but it is one phase. The good point is one phase, but it can be very complicated. Hydrocarbon, liquid hydrocarbon, gas hydrate, we can have a structure 1, we can have a structure 2, a structure H, or a combination of them. Okay, so you can see that one phase here, 2 phase, this is 3. This is 3 plus 3 becomes 6, and we can have salt 7, we can have wax 8, asphaltene 9, we can have ice 10, so we can have 10 phases in equilibrium. So you can see that how difficult it is. In this prediction, we use our commercial hydrate software or multi-phase software that will do comprehensive hydrate and phase behavior calculation. That will include hydrate, wax, asphaltene, salt, and different components. You can see that the option here you can do as calculation, you can do pressure, temperature, pressure, enthalpy, temperature, enthalpy, volume, pressure, pressure, entropy, and temperature, entropy. So we can do various calculations. And then on the calculation, we can go hydrate dissociation curve, amount of thermodynamic hydrate requirement, hydrate amount, how much hydrate will form. If we have kinetic hydrate inhibitor, how the hydrate phase boundary will shift. Asphaltene, model tuning, asphaltene onset, asphaltene content, precipitation curve, wax model, yeah, wax stability, wax content, and then equation of state tuning. If you have experimental data, we can tune equation of state, and we can plot hydrate phase envelope. We can do bubble point measurement, predict bubble point measurement. If you have the pressure, if you have temperature, bubble point pressure, and if you have temperature, it will give you bubble point temperature. And this is the dew point, and this is dew point. And here, if you have experimental data, we want to use it plotted against prediction, or we want to put it in the program. Our database has more than 20,000 data. Here is mixing the fluid, and here generating Olga tap file, freezing point, CO2, solid liquid equilibrium. So we have various options in the program. And these are the components that are in the program, and I'm sure now is a lot more. This is hydrate former. It is non-hydrocarbon hydrate former. These are non-hydrate former. This is organic inhibitor. That our result shows that isopropanol and normal propanol and ethanol, they take part in hydrate formation. So they are not 100% inhibitor. And we have salt here as well. So simple hydrate. Simple hydrate is when we have one hydrate former. And the objective is that to determine the hydrate formers of pure compound, and I showed the video, the curve earlier on. Normally, a small molecule form a structure 1. Molecules are like C3 and IC4, cyclopentane, and they can form a structure 2. And no compound is known to structure H on its own. So we won't have simple gas hydrate by a structure H. So an example here, the question is that calculate how hydrate formation in fact should be dissociation. That's what, as we discussed earlier on, for methane at 5 degrees. Okay, so now we have fixed temperature, and we want to find what pressure it will form hydrate. Is 638. So we know that. Okay. Now here is calculate hydrate formation for methane hydrate at 1000 psi. 9.51. Calculate hydrate stability zone for methane hydrate from 400 to 2000. Okay, so these are point calculation. 1 point. This is another point, and this is a range. So we want to determine hydrate phase boundary. So this is the range from 400 to 2000. Here is no hydrate, here is hydrate. So we can determine hydrate phase boundary for a pure compound. Another one, here we want to calculate hydrate phase boundary for ethane. And the same thing, 5 degrees, it's formed at 8.6 bar, and 100 bar, it's formed at 16.31, and the curve from 5 to 200 bar. If you do this calculation, this was for methane. This is for ethane. Yeah? You see that it's such a sudden change in slope. That is the point that ethane will change phase from liquid to from gas to liquid. So this is the bubble point of methane. Yeah. Okay. So you can see that bubble point of methane. This is ethane. This is ethane hydrate phase boundary, CO2 hydrate, and this is the bubble point of ethane, and you see that it crosses here. And the same is similar is for the C3. Okay, and this is a bubble point of C3. This is hydrate phase boundary of C3. And we don't have this for methane because vapor pressure curve for methane is far down in temperature. We know that critical point of methane is below 0. So we won't see it here. So methane is super critical compound here. And this is showing this curve on the graph on the logarithmic scale, so we can see it better. This is for CO2, and this is for this one is IC4. This one is C3. This one is C1, and this is nitrogen. Yeah, so you can see that different component would have, this is CO2, yeah, for pure compound. The question is that what will happen if we have a mixture? And here an example, nitrogen and methane 90-10, nitrogen and methane 75 nitrogen, 25 methane, 50-50, and here 25-75. What is expected to happen? You can see that this is pure nitrogen. Here you can see that nitrogen water, and then here is pure methane. And when you have a composition, different composition, you can see that as we increase the amount of nitrogen, hydrate curve shift to the left. You can see that. Here is no nitrogen. Here is 25 nitrogen. This is 50% nitrogen. This is 75 nitrogen, 25 methane. And here is 90%, the red one, nitrogen, and 10% C1. And then here is pure nitrogen. You can see that how the hydrate phase boundary shifts to the left as you increase the amount of nitrogen. So now instead of C1 and nitrogen, we have C1 and C2. Let's see what happened. This is 100% C2. This is 100% methane. You can see that if you have here, we have 50-50, the black line. You see that it goes across the pure methane. Yeah, pure methane hydrate phase boundary here. But you might say, why? Why it changes? And then here is 75% methane, 25% CO2. This is 95% C1 and 5% C2, and this is pure C2. The question is that why this curve for pure C2 can cross across the phase boundary? For this, we need to find out what is the phase envelope of C1 and C2 with different concentration. And this is shown here. You see that for 95% C1, this is the phase envelope. This one, 75% C1 would be this one. And you can see that this is a phase envelope. So at the condition of hydrate formation, the system is outside two-phase region of the mixture. So as far as phase envelope is concerned, these are gas. They don't, they don't cross two-phase region. Two-phase region is when they become liquid. Okay, so therefore, although pure nitrogen become liquid, pure CO2 become liquid, the mixture won't be liquid, and that's why we get a straight line here, and we can predict hydrate phase boundary. Okay, that's end of part 1. I stop here to see that if there is any question, and we continue this on the part 2. I stop recording.